All right, so this is the second review for test 3. In the last class, I went over line integrals, and for a line integral, what does a key point? First, we use a definition, use parameterization to find to evaluate the line integral. But in certain cases, if you can figure out the vector field, if it's line integral of a vector field, okay, then if the vector field is a conservative, maybe it's much easier to find the gradient of the function for the vector field, then evaluate the value of that little function, little f, at the two end points. So then you don't need to find the parameterization for the path to evaluate as an integral of the vector field around the curve. Now, today, we're going to focus on surface integral. Surface integral, oops, I know it's not connected. For line integral, for line integral, if it's closed curve on the plane, then maybe you should consider to use a Green theorem to change the line integral to a double integral. Okay. For surface, we have surface integrals, okay, of a function. Okay, a function defined on surface and integrated. And special case when the function is constant 1, then the integral constant 1 is give you a surface area. Then we focus on the surface integral vector field around the surface, which actually essentially is just the integral of a function, because it's a vector field, the inner product vector field with a normal vector. Then we have a Stokes theorem. Okay, the Stokes theorem says that the surface integral can be changed to the line integral can be changed to the surface integral. Okay, this is actually as a line integral along the curve, which is the boundary of some domain on the surface. Then you change. This is a generalization of the Green theorem, actually, right? Then the surface, in cases of the surface closed, then you have two options: either change the surface integral of the vector field to the triple integral. Okay, and this is called the divergence theorem of the divergence theorem of vector field. Okay, so otherwise you have to use a definition. If you cannot use the theorem of this listed on the page 1187, then you have to use then you have to use the parameterizations for the surface and use a formula for the surface integral. So let's look at all these examples. The first one I want to take a look at is from the summary. Okay, so we have the surface integral. We have this. Yeah, this is the surface integral. Yes, x squared z plus y squared z, and then yes. Okay, this is the integral of the function over the surface. The function is defined in the three-dimensional space. So so x squared z plus y squared z means the value of the function at the point x, y, z. Okay. So here s, yeah, this is actually just the surface integral s, f, and then ds, where f x y z, which is defined in the three-dimensional space, is x square z plus y square z. Okay. So actually, the function is defined in three-dimensional space, but restricted to the surface. Then you get a function on the surface, then you integrate it. Okay, so S is a part of the plane. Okay, Z equals 4 plus x plus y. That line inside the cylinder. This is a typical example I want to discuss here. So the surface, think about the surface is just some kind of a piece, flat piece, but it's inside the cylinder. Okay. Yeah, this is the cylinder. To solve this problem, we just use the formula for the surface integral using parametric equations. Right? The formula says, first of all, you write down the formula. The formula is going to be here's double integral, and the f x depends on x. Yeah, this depends on parameterization. The parameterization u and the v. Okay, and then here. Okay, so you write down that first, then you find out the parameterization u and v. Now this is a graph of some function z equals 4 plus x plus y. So you can use x, y, okay? But then you can also use a u and the v, 4 plus u plus v, okay? Here u is for x, v is for y, okay? And u square plus v square is less than or equal to 4. It's inside the domain, okay? Inside the disk, okay? So that gives you the image. Okay, so that gives you this piece of looks like elliptic. Okay, elliptic region in the space. All right, so if it's graph, we already know that. You don't need to waste time to redo the problem. It's going to be negative. The partial derivative of this function with respect to u is 1, and then here's negative 1, and then the last one is 1, right? Yeah. So remember the formula, a negative fx, negative fy, and plus 1, and the 1. Okay, so the length is going to be square root 3 of this vector. This is normal vector. Doing that, it's constant, the normal vector. It's not normal vector yet, but this is a vector perpendicular to the plane. Okay, unless you normalize it, otherwise it doesn't have a unit length. Okay, so this integral now becomes this surface integral of the function becomes a double integral. This is double integral, this d, right? And what is f? F is x squared plus y squared z. X squared plus y squared is just the u squared plus v squared. Z is going to be 4 plus u plus v. Okay? And then square root 3 and dA. Okay? Yeah, this is a z, this is a x squared plus y squared. Yeah, here x is a u, y is a v, and z is a u, 4 plus u plus v. Okay, so now to solve this problem, you use a sphere coordinates. Okay, u equals r cosine theta, v equals r sine theta, and I is between 0 and 2, theta is between 0 and 2 pi. So you get double iterated integral. And that is going to be 0 to 2, 0 to 2 pi, and here's r square, and here 4 plus r cosine theta, r sine theta. Okay, square of 3, and here r d theta dr. So what you can do, this is an iterative integral. You can evaluate. Let's write down all the terms here. 4 square of 3 and r cubed plus square of 3 r, so it's going to be r to the 4th cosine theta. Square of 3 r to the 4th sine theta d theta dr. And the integral of sine theta from 0 to 2 pi is going to be 0. The integral of cosine theta from 0 to 2 is also going to be 0. So when you evaluate, all you have to use is just 4 square of 3 times r cubed times 2 pi, so 8. Okay. Then you find the antiderivative. Antiderivative will be 2 square of 3 r to the 4th power, divided 3 in the point, and then 2 square of 3 to the 4th power. Okay, now it's possible to make a small computation mistakes, but if everything's in logic, it's clear, and you get most of the credits. Okay, so for a surface integral, if it's just a function, you don't have any theorem you can use, just the formula using the parametric equations, using the parameterization of the surface to evaluate the integral. Okay, you just use that formula to change the surface into a double integral. Okay, so that is a formula we're going to use. Okay, now for vector field, for integral of a vector field, actually the vector field, the inner product of vector field was a normal vector, okay, over the surface. Then you have two options: either you view it as integral of a function over the surface, like what we did, or maybe you can use other method to evaluate it. Okay, so there are two formulas you can use. The first formula is the curl of the vector field. This is the surface integral. It can become the line integral. Okay, so that means the vector field cannot be arbitrary. It's the curl of some vector field. Then you can use that. So, but most of the time most of the time, it's impossible to check whether the function is a curl of another vector field. Okay, so the most time we use this formula to evaluate is the line integral. Okay, the line integral can be evaluated using this surface integral. Looks like it's more complicated, but you have to carefully choose a surface. Then this is just generalization of the green theorem. If the surface is closed, okay, if the surface is closed, then you can change the surface integral to triple integral. Okay, so this is here is if S is closed, right? If S is closed like a sphere, it's not like a hemisphere. A hemisphere is not closed; you have boundary. Okay. Yeah. All right. So take a look at some examples from the book. Okay. Yeah. Yeah, such as like this surface integral. Okay. where f is going to be x or xz, right, minus 2yj plus 3xk. And S is the sphere. So it's closed. And was orientation, was outward orientation. Okay. So when it's closed surface, you have to be careful. You have two options. Whenever it's closed surface, you can use the divergence theorem to transfer this surface integral to a triple integral. Okay. If you don't use that theorem, you have to do directly. You have to parameter a sphere, okay, and maybe it's possible, okay. Then you become surface integral of the sphere. Let's try in two different ways. First of all, notice that this is a closed sphere, okay. It's closed surface, and this is normal vector, right? And you have to state that I will use the surface. I will use a divergence theorem. This is going to be the triple integral, which is a ball enclosed by the sphere, and this divergence of F. Who sent me? It's kind of too late. All right, so there's no need to record it to be on posted YouTube. Okay. So it's divergence of the function dv. Right. So using this theorem, you are going to evaluate. Yeah, E is the region enclosed by a sphere, which is ball. Okay. So let's try that first to see if which is better. Usually, whenever you can use a theorem, maybe the computation will be much simpler. Okay. So the divergence of F is going to be the partial derivative of the first term plus the partial derivative of the second term minus 2y. I think it's 2y not z. Okay. And then partial derivative of the third term, 3x. Right. This will be a function. So it's z minus 2 plus 0. Okay. Okay. So now it will be the triple integral, right? Of both. So this surface integral is going to be the triple integral z minus 2 dv. Okay. Then you have to use the spherical coordinate, right, to evaluate the triple integral. Okay, so you have to set up. So the spherical coordinate is, x is going to be right rho sine phi cosine theta. Always double check the picture. Yeah, it's going to be sine phi sine theta. Z is going to be rho cosine theta. And then the Jacobian, we call it Jacobian. Then that actually is a rho square and sine phi. Yeah. Okay. So we also know that this is our notation. Rho, phi, and theta is going to be, yeah, it's rho square, sine phi. Okay, this will be a 3x3 matrix. Okay. Anyway, so this is going to be rho is from 0 to 2. Okay, and 0. Okay, and the phi is from 0 to pi. It's complete sphere, so phi. And then theta is from 0 to 2 pi, and d theta. And what is inside here is going to be z 0 cosine theta minus cosine phi minus 2, and then here's rho square sine phi. Okay, So all I have to do is to, I think it's independent of theta. That's why immediately you will get rho square sine phi, rho cosine phi minus 2 pi dphi 0. Okay? And then the next one is to evaluate. Let's multiply this out. And there is a 2 pi here. I take it out maybe. Oh, how to do that? 2 pi minus 2 rho square sine phi dphi 0. Okay. So yeah. Then I think the integral of sine phi cosine phi is going to be 0 from 0 to 2 pi, because this is going to be half of sine 2 phi. Okay, the antiderivative will be the antiderivative will be negative 2 cosine 2 phi. Okay.
After that, rho cosine phi.
Low minus 2. Yeah, this is minus 2. Yeah. So when you look at this one, cosine 2 pi is going to be 1, 0, cosine pi. So first term is 0. So 2 is 4 pi, rho square, and the cosine pi minus cosine 0 is going to be negative 2. So I got negative 8 pi over 3 rho cube. Okay, finally, okay, so we got this number. Okay, it's going to be negative. Let's go back and double check why it's negative. So sometimes you can see that at the very beginning, it is going to be negative. Okay, why it's negative? When you look at this picture, okay, z, okay, z minus 2, okay. So is there any, yeah, when I see z minus 2, maybe get some idea so it's going to be negative because the function itself is always negative. Why z is between negative 2 and the positive 2? Okay, because it's a ball, inside the ball was radius 2. Okay, so with the radius 2, and that is going to be, yeah. So here's actually a quick way to do. The triple integral z minus 2 dv can be separate, right? Do you agree? All right. I claim the first one must be 0. You know why? Because it's this integral of the function z over the ball, right? The ball is the up half on above xy plane, other half below the xy plane. This is symmetric. And z above xy plane is positive, below the xy is negative. So positive and negative will be cancelled out. It's not a function. The second one is just a volume of the ball. You see so quick, right? Right? So it's going to be negative 2. The volume of the ball is a 4 pi over 3 times r squared, 2 cubed. So that's what we got. Okay, so yeah. So this is 8 squared. 8 squared is 64 pi. But this is the same answer. You see that quick. Right? Right? Usually, it's like a 1 out of 40 students will get this idea when they look at it. Most of them just don't pay attention, don't look at the function. Just, oh, okay, I'm going to automatically, after so many training, doing so many exercise, automatically just to use a parameterization, you know, okay, and solve the problem. It took a long time. Okay, I did not pay attention to. After I finish it, and I go back to I want to double check if this is a, you know, correct answer, makes sense or not, right? Why it's negative? Maybe my computation. I made a computation. Then I look at this when I try to explain to z minus it's going to be negative. Then say, oops, why not have to do that? It's just to separate it, and you can quickly evaluate the integral. No, if you do like this, it's obvious to me. You got the idea. So you can say a few words. Hey, these are the function actually in this above xy plane is negative. You know, the domain is symmetric. Okay, the function and the half of the domain is negative, the other half is positive. That will be cancelled out. Okay. So if you don't use the divergence theorem, okay, this theorem still can be solved. Okay, this problem still can be solved. I'll probably just set up an integral to see how it's working. Okay, and sphere. At every point is a normal vector. How does it look like? X, Y, Z. The normal vector is going to be it's a radius 2. So it must be the unit vector, but because this is a point on the sphere, so you have to divide by 2 in order to make a normal vector. So this is normal vector every point. Okay, the surface integral of this is going to be this surface integral, the dot product, right? And sometimes you're lucky, the dot product is very nice, and then you can simplify it, okay? Let's see. Where's my problem? I want to copy it. It's here. Okay. So f, let's calculate this. Okay, f is going to be xz minus 2y 3x and dot product x, y, z. Okay, so I get 1/2 x squared z minus 2y squared plus 3xz. So it looks it's a bad function. It's not. Don't look. Sometimes it's nice. Cancel out. Okay. So this becomes a surface integral of that. Okay. But you still have to how do we change it to the surface, right? It should be in the double integral. Okay. This is my opinion. It's probably canceled out the integral of you see like this, the integral of this is integral of this. The surface, the sphere, right? So z is positive up hemisphere, negative lower hemisphere, right? For any given point x, y. So I think this is going to be canceled out, and that is also going to be canceled out for any fixed y. So this only becomes by the symmetry, right? Then what? But also by the symmetry, s x squared ds is going to be, it feels so nice. Do you agree? That should be all equal. Another symmetry. Using symmetry, I try to avoid using the parameterization. Okay? Great. So I believe that the sum of them, right? So this is they're all equal. That's why this becomes 1/3 of x squared plus y squared plus z squared ds. Okay, and this one on the sphere, this is going to be 4 ds. Okay. I'm trying to see if I can get the right answer here. xz, the integral of x times z. The integral of x times z is going to be negative, going to be 0 now over the sphere. I think so. So I'm trying to get this. Okay. So this is going to be 4/3. And divided by this is a surface integral of the area of the sphere. So it's not working because I get a different answers now. I have a 9 in the denominator. Yeah. So, but this is correct, okay? If the just integral of y squared is correct, integral of y squared is going to be the integral of x squared is going to be integral of z squared. That's same, okay? Because the x, y, z are in the equal position. So that's the reason you add them together and divide by 3, okay? So now this is going to be the area of, sorry, I think it's correct. The area of the sphere is a 4 pi r squared, right? R squared is 2 squared, okay? So this is the answer, okay? So this is the area. I think it's correct, yeah. It's not, the volume is divided by 3, the area is not divided by 3, okay? 4 pi r squared. All right, so this, when you put it back, there's negative sign here. When you put it back, my integral will be negative, right? So this integral f ds is going to be -2, right? Remember, this is -2 and multiplied by I think this is the same answer. Extra 2 here? So something's wrong. Extra, maybe I missed, oh, so that was divided by 2 here. Okay, so that's no extra 2. Okay, yes. All right, so it's negative 8 square pi divided by 3. All right, so this problem I using lots of symmetries. I cancel the terms. So integral of x times y over the sphere will be 0. Just like an integral, you know, if you see an integral of this one, x cubed dx, you don't even waste time. This is going to be 0. Why? The function is symmetric. As the functions are other functions, right? Other functions, so the interval is also symmetric. So there will be positive, negative part will be canceled out, right? Like this one will be canceled out. But then for the sphere, it's the same story. If this is a sphere, okay, if this is a sphere, then anything that's added, okay, as long as you see x cubed, something like that, and you can put a z there, doesn't matter. Okay, ds, that's going to be 0. Okay, why? This is an odd function with respect to z, because when you look at the sphere, okay, for every point x, there's a value of the function at this point and the value of the function at that particular point. They have the opposite sign. Okay, they have opposite sign. So when you integrate, negative, positive, that cancel out. Okay, that's the reason. And this function also, from the front side to the back side, also is opposite. You know, they have opposite sign because x changes sign. The -1 and +1, right? X cubed. So even I change it to x squared, it still be 0 because its other function with respect to z. Okay, it's also going to 0. Okay, on the sphere. Okay, so using symmetry, it's important to save you time to the computation. Otherwise, for this particular problem, you have to find the parameterization for the sphere, and then you have to do the cross product, right? And it's very complicated. You have to stop there. You cannot, when you multiply it out, you get so many cosine, sine, cubes, you know, yeah, you can imagine, yeah. So otherwise, you have to find the parameterization for the sphere, that's a phi and theta, then the surface integral of this f, right? ds. This f represents our function. Where's my function? Half of x squared z minus 2y squared 3xy, right? So for that one, yeah, f is half of x squared z minus, okay, I try to memorize all this number. Negative 2y squared plus 3xz. And this is a function. Now, if you use the parameterization, how do you do that? You will get phi is between 0 and pi, theta is between 0 and 2 pi. And here, f, you have to evaluate this, okay? Then here's phi dot cross product, and the d is theta d phi. This is the length, okay? I think this gives you sine phi, but as a term, when you replace x, okay, so here x is going to be 2 sine phi cosine theta. That's parameterization for sphere, not for the ball. Y equals 2 sine phi sine theta. Z equals 2 cosine phi. And you have to put it into here. You see that you will see lots of trigonometric functions. It's complicated, yeah. So the best way to solve this problem is the divergence theorem. The second one, it's not easy to handle, is using symmetry of the domain of the ball. Okay, but sometimes not lucky. You know, the function is not that great, so you cannot use this second method. But this is a standard parameterization. But remember, when the surface is closed, okay, the best way to use to evaluate is using the divergence theorem. The same story here. If the line integral is on closed curve, right? Then use the green theorem. Okay, using the green theorem. Okay, even that curve is in the space. If that curve in the space, you still can use a. You can use a Stokes theorem, but it's essentially it's a green theorem. Okay, so for example, this will be a little bit challenging. You know, it's three-dimensional. Okay, I draw the curve on here on the sphere. This is the curve C. Okay, it's a closed curve, and how do I do that? It's a z equals 1, and sphere is x squared plus y squared plus z squared equals 4, right? So that cut, so you get circle C, and then then you have the vector field, which is going to be x, y. Just give a simple vector field. Evaluate this line integral. Right? How do you do that? right? So I describe the curve on the sphere. This is a curve on the sphere. Now you have to parameterize it, right? This is line integral in the space. Okay, the vector field is going like this direction. Okay, so now is it perpendicular to the tangent? It's going to be 0. Okay, so I cannot change. Yeah, I'll make the, so this is clearly it's going to be 0. If we understand this line integral, okay, why this is a f dot t ds, right? And look at the tangent vector. The tangent vector is this, and this f is we call a radiant vector from the center going out, and this is a f is normal vector. The normal vector of the sphere will be perpendicular to the tangent vector to any curve on the sphere. So it's clearly it's going to be 0 because this is going to be 0. Okay, because since f is normal vector, but if I change f to just x y and 0 is always yeah. If how about this? If I change it to 0, 0, z, okay, at that particular, and then this is now going to be 0. Okay, as this is a vector field is going up, right? Always point up, right? So in this case, there are a couple ways to do. You can use a Stokes theorem, right? You can also use the formula using parameterization for the curve, right? So my suggestion is you can solve the problem either way, okay? So how to parameterize it? C, right? It's the intersection of these two, okay? So intersection of these two, this is the radius 2, right? And this is going to be, here is going to be 1, the height, right? How about that? Here's 2, right? Right? Can you figure out the angle, right? I think the angle is going to be a 60 degree. That will be 30 degree. The special triangle. All right, so the other side will be square root 3 over, this r is going to be square root 3 over 2 times 2. So it's just a square root 3. Right? So the parameterization is x is going to be square root 3 cosine theta. Y equals square root 3 sine theta. Okay? And the z is always equal to 1. So this is a parameterization for the curve. And then you can use that formula to solve the problem. Okay? So let's work out. So the line integral is going to be from 0 to 2 pi and f dot prime theta d theta. Okay? So f is nothing but 0, 0, z. At that particular point, z is always equal 1. R prime consists of the 3 components: negative square root 3 sine theta, square root 3 cosine theta 0, and d theta. Okay, and multiply them out. It's going to be 0 again. Okay. Well, it's 0 again, no matter how hard I choose. If I choose another one, I'm going to choose another one. Otherwise, it's too trivial. I'm going to put a y here. Okay. So this is no longer, yeah. So this is a y. If it's y, then at that particular point, it's going to be square root 3 sine theta. Okay. Yeah. then that when you multiply this out, and it's going to be square root 3 times square root 3, sine theta, cosine theta, d theta. Again, this is going to be 0, but the function at least is not going to be 0. As the function changes signs, okay, this is still going to be 0 anyway. So it's possible a problem like that be on the test. You know, but if you want to use the Stokes theorem, you can solve the problem. The Stokes theorem, you have the two choices: which surface you're going to use, bounded by the circle in the space. Okay, so it could be the disk, it could be the portion of the sphere, because they share the same. Look at that, right? It could be either this part or this part, right? Yeah, right. And then clearly the disk is a simplest surface, right? Enclosed by this curve. That's a circle. Circle can be viewed as the boundary of the sphere. Okay. In that case, you can compute it using the Stokes theorem, because this is C f dot dr, right? It's going to be the surface integral, the curve of the vector field, and df. Okay? And I prefer to use the disk, because the disk, I know the normal vector is just the k. Okay, and all I have to do is just compute the curve of the vector field in the space. The curve of the vector field is going to be, yeah, I'm going to use this S, okay, S, using this. So the curve of the vector field is ijk 0, y, z, no, this is the last row. Okay. And then let's look at the curve of the vector field. I is going to be, it's going to be 0, I minus, it's again 0, j. So the curve is going to be 0. Okay, the curve is going to be 0, right? Yeah, the curve is going to be 0. Okay, so the curve is going to be 0. Then therefore you don't need even, doesn't matter which surface you're going to use. Okay, so this otherwise I choose that surface. Okay, that's clear. Now why this curve is that function is a curve of the vector field. Okay, remember, okay, recall the theorem. If this is going to be 0, right? Then f is on the whole R3, okay? Then f is conservative, okay? Right? That's where how do we check whether a function is conservative? So that means it's going to be gradient of some function, okay? For some f. Okay, they're all connected, right? So what is f, right? So the gradient of the function, this is going to be 0. This is going to be y. This is going to be z, right? Because my f is 0, y, z. I choose that. So does that such function exist? It's obvious. F is going to be half of y squared plus z squared. Yes, that's the main reason. Yeah. It's easy to solve that system. No one, you know. So if the vector, if the vector field, the curve of the vector field is going to be 0, and then the integral is going to be 0 of along any closed curve in the space. Yeah, it looks like, right? Yeah. So if the closed vector 0 in R3. Then for any closed curve in the space, the line integral dr is from 0. You know why? If the curve is boundary of the sphere, then by the Stoker theorem, if it's not boundary, it's not a sphere, then the closed curve can be like that, right? You have a starting point and end point. Okay, so this integral becomes this integral actually, because f is going to be greater than some function. So this is the starting point. This is also the ending point. So that will be f, right? That's why that's the same point, because it's closed curve. Another explanation. Okay, but if you use if it's a spanned by, if it's a boundary of some sphere, then this can be viewed as or by the Stokes theorem. Right? And this is also 0 because the curve is 0. This is it. Right, the couple reasons. All right, so now let's move on to the next problem. It says that use a Stokes theorem to evaluate this line integral, and where the function is defined in the space x, y, z, x, y, I, plus y, z, j, plus z, x, k, right? And the C is a triangle with the vertices right, oriented counterclockwise. As viewed from above. Right. So here's a picture. It's in the space, right? X, Y, Z. Where's the point? This is the first point. That is a second point. That's the third point. This is my plane, my surface. Okay, it is oriented in that form. Okay, that's a curve C. So you are given this line integral. You can evaluate this line integral directly, no problem. Okay, but yes, the curve consists of 3 pieces. You have to one by one. Okay, if that's the C1, that's the C2, that's C3. This line integral is going to be the line integral C1 and the line integral C2 and the line integral C3. I think this three-line integral will be probably end up with the same result. Why? Because the function is symmetric. It's like x, y, y, z, z, x, you know, right? So along each line, it's not too bad. You can do that, right? Along each line, the product is going to be, look at along this line, look along the line on the in the xy plane, okay? Then the tangent vector, the z component is going to be 0. Okay, where's the function? I think we can do that using, it's take a little bit more time. Yeah, you can evaluate the integral of the product, okay? Yeah, let's finish the first one. Okay, I'm going to show you how to do the first one. So for the first one, you have to parameterize it, right? So how do you parameterize it? See, let's start from 1, 0, 0, 1, and the t, the difference of those two vectors. I think this will be -1, it's positive 1, okay? The difference of two vectors, and this is a, okay, when t equals 0, you get a starting point. When t equals 1, you get 0, 1, 0. Okay, clear. Okay. So the derivative is going to be this, right? All right. So I have to evaluate this function, this vector field along this line, and clearly, since since z is 0, x is going to be 1 minus t, y is going to be t. Okay, z is going to be 0. Okay, when you look at this function, you find out, look at this vector field, you find out only the first term is non-zero. So it's 1 minus t times t. The second term is 0 because z is 0. The third term is also 0. It's not too bad, okay? Then the dot product is going to be here from 0 to 1, right? So the dot product is just equal to the integral of that. It's negative 1 minus t dt. Okay, so evaluate. It's going to be t squared minus t dt. T squared minus t. So the entire derivative will be, it's going to be negative 1/3 minus 1/2. It's negative 1/6. So by the similar argument, I'm pretty sure the rest of them same. Okay. Yeah. So my conjecture is multiplied by 3. So when negative 1/2 should be the answer. Okay, because on each. Now we're going to buy the Stokes theorem. Using the Stokes theorem. Using the Stokes theorem, it will be the surface integral, and the surface integral here, the curve of the vector field and ds. Let's compute the curve of the vector field first. Right, the curve of the vector field is going to be ijk. The vector field here It's going to be x, y, y, z, and the zx. Right? The first one, I think it's going to be y. Yeah, the cross product. Yeah. Then the second one here is going to be minus, that's going to be z. Yes. And yeah, negative plus it's minus, okay, minus x d xk. Okay, let's double check the sign, okay? Why there is a positive sign, negative sign. All right, so the first one, I think it's also negative, yeah. Yeah, negative. Okay. So you have all the negative signs, negative yi, negative zj, and the negative xk. Okay, so this is a curved vector. Okay, look at this picture again, the surface. Okay, here, this is surface. The normal vector is already given. Okay, the normal vector. Okay, so the surface, what is the graph of surface? The graph of surface is going to be x plus y plus z and equals, I think it equals what? Do you agree? Yeah. Okay. First of all, equals some constant because the normal vector of this surface at every point is going to be 1, 1, 1, square root of 3. Okay? This is a normal vector at every point. Right? So you get all this data. Okay? So now we're going to evaluate the surface integral. Not too bad. According to above computation, around at every point on the surface x, y, z, my one here is y, z, x, right? Dot. The normal vector ds is going to be the normal vector s ds. Right? It's going to be square root of 3, 1, 1, 1 ds. So we can compute this dot product first. Then you end up with just y plus z plus x divided by square root of 3 and ds. But over that surface, at every point x, y, z, x plus y plus z is going to be 1. Okay? So you take the constant out. So then you get the surface integral of the constant, which is going to be the area of the surface. Now, this is where you have to apply geometry. Okay. So how do you find the area of the triangle? How to find the area of this triangle? Do you have to use a higher advanced mathematics to start, calculus 3 to find the area of the triangle? You can pretty much write that, no problem, right? Because this is a graph of z is going to be 1 minus x minus y, right? And then the domain is this part, right, d. You can do that, but it's not necessary because this is an equilateral triangle. Equilateral triangle, remember, for the equilateral triangle, this is a good exercise for 7th grade or 6th grade students, okay? Okay, so for equilateral triangle, how to find the area expressed in terms of edge length, okay? So when they do that, everybody knows that area formula, A equals half of A times H. But can you find H? Yes, because this is special triangle, 60 degree. 30 degrees. So h is going to be square 3 times a, right? So that's why you have the area formula for equilateral triangle a. But what is our a here? By the Pythagorean theory, a is going to be square root 2 because this is a 1, 0, 0, right? This is going to be 0, 1, 0. So the distance here is all equal 1, so that's why it's square root 2. Right? So now, after you simplify, it is going to be square root 3 over 2. That is the area of this triangle. Right? When I put into here, this surface integral is going to be, right? What I got here? I got, oh, great. You see, I already have a, I already have a 1 over square root 3, right? It's the area of the sphere, of the triangle. And that's going to be, right, -1/2. And that is the answer I conjecture, right, at the very beginning. You remember? I use this method. I find, I evaluate this is C1. I evaluate this line integral along C1. I said that along C2, along C3, you should get same answer. So -1 over 6 multiplied by 3 is going to be -1/2. Right? So that is the answer should be the line integral. So use Stokes theorem, you can solve the problem. So we actually, we do not parameterize this surface. Okay, the reason is it becomes the integral of constant 1. And all I had to do is just find the area of this surface. I don't need to parameterize it. Okay, if I want to parameterize it, I still can get the same answer, would be square root 3 over 2. Okay, where's the square root 3 over 2 from? I think it's from, yeah, you use a parameterization for this. That's it. I think I already did a divergence theorem, surface integral, and yeah. So when you go home, make sure you go through the notes, okay, and redo the problems, and you have to summarize the ideas and so organize them. Otherwise, it's hard to memorize it, and you have to practice. Otherwise, you cannot find the best way to solve the problem.